Okay, I think it's time to start the second session, and I'm Hideki Nagano from NICT in Japan. I'll chair this session. Welcome to the AI-driven network working group. In this session, we have three speakers. And the first speaker is Tin Yuan, University of Göttingen. And the title is when Artificial Intelligence Meets Networking. All the ready? Okay. All right. Yeah, we can see your slides. So
Yeah.
yes, would you please at the
Okay.
presentation?
Okay. Thank you for introduction. Okay, so I'm Dr. Tintin Yuan. It's my pleasure to have this chance to discuss our work when AI meets communication or networking. So in this talk, I'm going to first cover the basic idea with the relationship between the AI and the communication. And then I will use one of our work on video analytics to illustrate the relationship and the trend of AI technology deployed in our smart city. We know the smart city is coming, right? And our city is smarter and smarter with the support of AI technology. For example, for the traffic management, the monitoring, and the situation of the traffic, including the UAV delivering the goods and support the network connection for emergency. Okay, so let's say what the relationship between AI and the communication. From one side, AI rely on the efficient communication. We can see this figure that from the sensing layer, the data is collected by many kinds of the sensors and like the cars, vehicles, cameras, and the citizens. And after the data collection, when you transfer the data, right, to the application layer to support the AI technology. And this one, we call it communication layer. No matter which kind of technology you use, like the LoRa one, the LTE, or the modern like 5G and 6G. Okay, so data it need to collect it, use the communication. Furthermore, the learning itself need the communication, like the federated learning, speed learning, and the multi-agent reference learning. We call it MARL for short. And some of the technology also rely on communication for inference, like the split learning and some of the multi-agent reinforcement learning. Okay, so on the other hand, the AI play a very important role in enhancing the communication. For example, the AI technology can be used for the routing, the traffic management, and the congestion control. Okay, so now we are entered the age of the AI plus IoT. IoT is the Internet of Things that connected everything together use the communication system. So we say it AI plus IoT, we say it is AIoT. So why AIoT is needed? We can say AIoT bring many benefits in different layer. From the sensing layer, the AI can do this. AI can help the sensor and devices to improve the efficiency of the data collection. For example, one of our work is on the UAV trajectory planning. It can help the UAV to sensing the environment more efficiently. And in the communication layer, we can say the AI-powered networking system can enhance the data transmission, such as the traffic control or the path planning. Okay, from the top layer, application layer, AI assist analysis and applications can enhance the data processing, like improve the security, quality of the service and reduce the latency. For example, the ULO is well-known technology has been used for the object detection of images, which only take milliseconds to do this. And the PPO is proposed by the OpenAI. It can dynamically set the sequence of action, for example, the traffic management or the traffic light control. So let's say what's the challenge when enter the AI IoT age? So the first one is how to offer fast response and real-time analysis. We see previously AI technology is put in the cloud, okay, which is around the clients is on the edge. They access the AI technology need to pass one by one helps to enter the cloud, so which takes more time, like 30 to 70 milliseconds. We see the figure in the right. Okay, so more and more modern applications require latency lower and lower from the hundreds millisecond to several milliseconds. So AI put on the cloud is not it cannot support this kind of applications. So one of the trick in nowadays is AI is moving from the cloud to the edge and the local. You can say from moving this one, this trade will reduce the latency much lower, meets the requirement of modern applications. The second challenge is how to share one AI service and components among multi-clients, as more and more clients are joining into sharing one of AI technology or service. So Chit 2 is how make AI scales to support multi-clients. And note that to support for this tree, we have two aspects. One is the scalability for clients. Let's say when in increasing number of clients, so we need to maintain the performance and the efficiency. And secondly, the joint clients, there might be heterogeneous, okay? So they have different software, hardware, and the conformance and the requirements. Okay, third trait, the last trait is how to coordinate multi-agents. As we say, the AI is moving from cloud to the edge and the local. So the lightweight AI technologies are included, and multi of the agents need to coordinate with each other to achieve the complex task. Okay, so the third trait is to transfer from the independent AI technology to cooperative AI. So cooperative AI, we also call it cooperative intelligence. So from the beginning, they are independent and decentralized mode. The agent work lonely, okay? And now it's increasing gradually to hierarchical mode or networked mode. The difference between these two cooperation mode is that hierarchical mode has a central node. Okay, so this guy can coordinate multi-agents. And the network mode, the agents are equal. Okay, so they connect each other, communicate each other to achieve the task. Let's say example on the video analytics. It's one of our main work in the past 2 years. So the AI-powered video analysis is very important technology for smart city that the devices can put on the street to monitor the traffic and like for the road collection detection, for the smart control of the traffic light, and finally can do the traffic pattern analysis, and later can support the urban planning of the manager. So this our work support that the EU Horizon funding. Okay, so we are planning, deployed multi-cameras in the main street of the city Göttingen. Okay, so at the first stage, we are going to put 4 cameras. We say the video analytics will collect the video, and the video had a profile like the frame rate. It's the frequency of collecting the images or the frames. I say to achieve real-time analysis, we need to meet the latency, say the right column. However, we analysis before the delays of deploying AI technology, right? So we say to meet this latency, we need edge AI at least. So we put 4 edges near to the cameras. So, and additionally, we put 1 centralized guides to collecting final data to store metadata there. Okay, so that's the one trait. the first trade, AI moves from the cloud to the edge and or even to the local to support low latency of AI response. Say when the camera collect the data, okay, it need to encoder them to bit stream and then transfer to the edge devices. And edge devices do the decoder to frames, and the inference use the AI technology and give the results. We say this one, the communication is very important, right? To streaming the video to the edge for analysis. And now the traditional pattern, you say the AI is put on the application and analysis on the edge. So the problem here, when we do the communication, the bandwidth is a limitation, which creates low quality of the video. We see the results. The high quality of the video, we can analysis with high accuracy, but when the video decrease the quality, it obviously decrease the accuracy, which more clear see the table. To avoid this, we do a work on this video upgrading like the ACC decoder. So the basic idea is say we upgrade the decoder on the edge. So we want to increase the quality of the video. Okay, this technology we use the super resolution, which is also AI technology to improve the quality of the video. However, super resolution obviously can increase the accuracy, but at the same time, it also increases the latency much beyond the real-time analysis requirements. That's what we don't want to see. So in this way, we also include another part to accelerate the analysis. We use based on the reinforcement learning accelerator to wisely select part of the frame to do the super resolution. Okay, so as a result, we can say our ACC decoder can achieve much higher speed up and the accuracy improvement. Okay, and let's say the stage 2. Stage 2, we want to place more cameras in the city center to trace the pedestrians tracing. Okay, and 4 cameras put in, and at the pedestrian, they work speed it's much slower. So we can just put 1 edge devices and let the 4 cameras to share these devices. Okay, so this is the Chit 2. The AI need to scale to support multi-clients. Say 4 cameras share 1 edge, AI edge. And let's say the things we achieve. The multi-camera here and they are streaming videos to the edge. And the edge need to do the analysis, and some of the frame need to also do the super resolution to increase their quality of the video. However, challenge is there. The super resolution is content-based. So we cannot use one general super resolution model to achieve multi-camera contents of the camera super resolution. So this incurs a lot of cost here. So our idea is to do another thing like the more and more smart cameras are included, so they can do a lightweight onboard AI on the camera. So we do this, we propose hybrid encoding. Okay, so we can select some of the frames to send the high quality of the frames plus some low quality of the video together. So we put the AI technology on the sensor side on the camera to select the frames to send in high quality, and also put the AI on the end on the edge to do the analysis. Okay, so here we see that another challenge is the camera has different contents, right? So some of the camera has dense content, usually needs higher bandwidth, and some camera has lower content, lower targets, and need only low quality of the video, so it can save some bandwidth here. So in this way, we put also AI technology on the communication to let the networking slice the networking resources widely according to the content. Okay, so now you can see until now we put AI in the sensor side, in the communications, and also on the application and analysis side. Okay. So this is we'll do this. We found that if we independently training the model to do the network management and under the sensing side, we say the performance is not that idly because there's some space, say the optimal performance with the independent training. So we put a joint training model, use the bi-level optimization reinforcement learning. Okay, so we set a high level to be the network agent, which to coordinate the local agents. Local agent is the cameras to work together. Okay, and the local cameras based on their partial observation of the environment to maximum their utility by themselves. Okay, and the network agent can coordinate, has a bigger view to achieve the fairness. Okay, so finally, the B-Swift our work has good performance, and compared with the ACC decoder, it's our previous work. We say it has better scalability and ACC and accuracy. And this is a trick from the independent to cooperate AI. They are training together in different layer, communication and the sensing layer. And this one is a hierarchical mode as the network agent. You can see more like a coordinator as a central node. Okay, so they are in different layer. It's a hierarchical mode. And the last stage, we are going to employ more and more cameras, and some of them can be in the movable devices like the UAV or the vehicles. So in this stage, we need to achieve the scalability, okay? And the more cameras may join in and may because they have more mobility, so they can move to another region as they like. So we do this, we can cluster the cameras based on their states and like the profile, the bandwidth, and the content of the features, and cluster them into group. And based on the group, we let the controller, is the network controller, to vastly slicing their bandwidth. It support the scalability and the hierarchical of heterogeneous of the cameras. And beside this, we say the hierarchical mode, right? And beside this, we also can do the network mode that the agent need work together, working the network the way in the same level. And this one is like the agent, the camera, or the manager may be in the different range of the city and has its own partial observation of the city. So the agent want to share the information between each other to make more wisely decision-making based on a broader information of the whole city. So the agent want to share the message, and this one will, if they use some AI technology to wisely sharing their message, they will create their own communication protocols while learning. We say it's learn to communicate. The content they need to learn includes when to communicate and how to communicate, quite like creating their own language, and with whom to widely sharing the message, find the targets. Okay, so that's what we do at another work to create the cooperative intelligence. Okay, in this work, we propose DACOM. And DACOM, you see it in the architecture. It includes the message encoding and create their own way to communicate. And they cite a timer based on the TimeNet, which can, based on the awareness of the networking system, like the delays and the bandwidth of surrounding environment, they can wisely select the time they want to wait for the message. Okay, so finally, the DACOM, you can see it achieve better performance no matter how the environment, like the delays of the environment increasing or decreasing. Okay, so it can achieve much more stable performance than other approaches. via the networking system awareness. Hey, as a conclusion, we have do many works in different layers, including application layer, we do the video analysis, and the communication layer, we do the network control, path planning for routing. And in the sensing, we do the UAV trajectory planning to have more efficient of data collection. And in the AI algorithm layer, we do some like corporate intelligence, also propose the privacy protection at when the agent sharing the message, there's some chance they will make the privacy leakage. Okay, and so let me give a conclusion of this talk. At the beginning, we discussed the relationship between the AI and communication. We know they are quite rely on each other to achieve the better performance in the smart city. Okay, and also that results in our inter of AI AIoT. Okay, and the AIoT is proposed to achieve the many different layer of improvement like the sensing, communication, and the analysis of application. And later, I use one example of our work is the AI-powered video analysis to illustrate the Chit and how we solve this challenge in the AIoT. And the Chit includes the AI is moving from the cloud to the edge and the local to reduce the latency and achieve real-time AI service. And the second trait is AI need to scale to support multi-clients, okay, to make the AI scalability. And the trait three is that AI is based on the communication. They are transferred from the independent to cooperate way. However, there's more challenge how to achieve this to make it more robust to the environment, like the network latency. We also propose some idea how to solve it, and also the privacy protection over this cooperation. Wait, that's all for this this talk. Thank you for your attention. And any questions?
Thank you very much. Are there any questions? Okay. So I have one question, and for the in the part of the cooperative intelligence, cooperative AI parts, and each that system and just the bandwidth of the for the each camera to minimize the latency of the camera, right?
Cooperative, you mean the constraints of cooperating intelligence, or?
Yeah, and I would like to ask what does the system optimize what kind of parameter does the system optimize?
Uh, okay, so yes, the bandwidth also like constraints. Some of the work optimize this based on these constraints. And from my view, it's more like the how let the AI technology adapt to these constraints. Say, how if the bandwidth limited, then the video will encode it in low quality, right? So that can save some bandwidth and meet the latency requirements. And for the network, the mode, it's more important that the agent to sensing the bandwidth or the delays of the environment, then they can wisely to select, for example, to communicate or not communicate because the latency is too much. So they maybe reject to communicate. Okay, so it's a space to wisely to choose communicate or not based on the networking system states.
Okay, thank you. Is there any question? Okay. Okay, thank you very much.
Thank you.
And the next speaker is, sorry. A Moon, and the title is Reinforcement Learning Based Traffic Signal Control in Urban Network of Bangkok City. Oh, is that ready?
Yes, I'm ready. Okay, let me share my screen first.
Yeah, please.
Okay, can you see my screen?
Yes, good. Oh,
Okay,
would you search the presentation mode?
okay. Okay, now is it okay?
Oh, no, the change the display setting, and now we can see the presenter mode.
Oh, okay, sorry.
Oh, okay,
Okay.
good. Please start it.
Okay, good morning, everyone. Thank you for inviting me to present for this Apan57. Sorry for like online presentation. I can to the Apan community. Okay, so today I would like to present about Rama full model project that we have tried last year. So and related research work that I'm trying. Okay, so the title is like reinforcement learning based traffic signal control in urban network of Bangkok City. So currently I'm research assistant under the supervision of Professor Chowdik as well. I think Professor Chowdik is sitting over there. Okay, so today, in this presentation, I will talk about the Rama full model project and also like type of the sensor that we have configured in the Rama full area, and also like before we try like our research, how we do social experiment, and also research. I will present about research case study area and simulated area. Okay. So in this project, Rama full model project, the period is like we started 2019 and hit 2023 last year. I think exactly it took about 3.5 years. So why we focus on this road? Actually, Rama full road, it is along this road. So it is the like busiest road in the Bangkok city. So we mainly focus on this road, and also we separate three distant areas: western part, and also middle part, and also eastern part along this road. So in the western part, it is related with the Satong Road. I think Bangkokian know this road. It is the Satong Road, so it is related with Ramapur Road. So actually, this area is Satong area, so it is also busier district area. While here, vehicles, most of the vehicles came to this area for their work, and also around this area there is a lot of like university and also like like so this western part also the busier area, and then we focus to the like middle area. Here we call the like Pasamrak Masuk area. Actually, in this area, there is a like fresh market and also like piers around in that area. And in the like eastern part we call like Onut, Prakano area. There is like it is also like a small, how is it, small popular city in Bangkok. So most of the like it is also popular area. Most of the people are working around area, living at this area. So we mainly focus this three western, middle, and eastern part area along the Ramapur Road. Okay. So actually we try to like survey on those area. I will mainly focus on the middle area. Okay, here are like we call the Kasamrat area. especially a Cassandra gridlock area. Why it is like a gridlock? Because for example here, like you can see the it is like traffic flow pattern here. So traffic flow and also this yellow road, it is the like expressway. So most of the vehicle came to this area and pass this area and go to this upper area. It is the like Sukhumvit area. It is also like PCS district area. So so that's why vehicle pattern is like flow the cycle. It is like a loop. So so that's why we try to analyze and survey in that area. And also in the middle area, it is another small gridlock. It is we call it is like Masuk area. Here also it is the pattern is like a loop, and the big Casamrat area a moment ago that I told, and also that small Masuk area, they are attached each other. So when vehicles congested in that area, it also affect on the like the big Casamrat area. So that's why we trying to like survey on that area together to solve how can we solve vehicle flow smoothly on that in that area. Okay, another one is the on-route bottleneck area. It is the eastern part of the Ramapur Road. So here is like we found that there is a like a bottleneck over here. For example, there is a like a Big C supermarket in that side. On the other side, there is a residential. So and also another root cause is there is a pedestrian crossing in front of Big C supermarket. So because of that pedestrian crossing, vehicle cannot move flow in that area because of vehicle from the Sukhumvit road want to move in that area and also want to go outside from that area, something like that. And also there is a like vehicle parking under the bridge over here. So like vehicle pattern is like it is also loop bottleneck. So that's why we focus on that area as well, on node bottleneck area. So okay, so I will show about we trying to inject that data in Sumo simulation of urban mobility. Actually, we use like data from the BMA, Bangkok Metropolitan Association. So we use that like an collected data and injects to simulation of urban mobility. Okay, so here you can see that vehicle moving on that area, and it is like a loop pattern. For example, I will show again. Okay. Okay, so it is the only bottleneck area injected in the Sumo. Okay, so then I would like to talk about the type of the data source in Ramapur model project. Firstly, we already have the this kind of data from the province data from the IT company, and also graph data and incident data. We already have those data, but in the Ramapur period, we try to configure a new sensor. It is like a CCTV camera and also Bluetooth data. And also this is also CCTV data from the NDIS company. And also we trying to configure the like signal control sensor. Okay, so from those sensor, actually we collected vehicle count. Mostly we collected vehicle count and also like travel time and speed. And also Q length and pan ratio data from those sensor type. So the objective is like we collect those data from those sensor, and also we try to like find the root cause on those western part, middle part, and also eastern part area. And also we trying to find out the how to like how to try to solve the gridlock pattern and also bottleneck pattern in those area. Okay. Okay, here is the like location of the signal control sensor along the Ramapur road. I think we trying to configure total 10 signal control sensor along this Ramapur road. Here is the like signal control sensor location. Okay, so it is only this part is the like my research focus area. It is the middle part of the Ramapur road. Okay, as I said before, it is in the middle part of the area, and also it is Ramapur road is related with the Satong road as well, and also here is the like expressway. So we mostly vehicle came to this area from this expressway, and also Ramapur road and Satong road, something like that. And also this part is the logistics zone here. There is a pier and also custom department around this area. So like logistic trucks move around this area, and also vehicle from the like expressway went to pass this area and they go to the busier district area. It is a Sukhumvit area, something like that. So that's why in my research area, I want to solve this area. The objective is like I want to like how to say, I want to optimize throughput in that area. So so we have like AI technology to solve this area, right? So I use the AI technology to control the traffic signal and to optimize throughput. Okay, so this is the example of the simulated area. Okay, so here I show with the like average speed of the edges in that area. Okay, so you can see that like with the color coded for the road, like which roads are like highly congested, something like that. Okay, so like in the real world, we have tried to install the sensor, CCTV, AI, Bluetooth, and like grab something like that. So okay, so in the simulated area, how can we imitate those type of sensor? In the like in simulation of urban mobility, we can try we can install like lane area data. It is the same as the CCTV cameras as in practice. So that's why in my like research, I try to install lane area data to detect number of vehicles and also to detect like jam ledge and also speed, something like that. So over there, like I mainly, because here is the in real case it is like a 5 intersection, but here also like I try to like imitate one virtual intersection over there. So total 6 intersection in that area. So here you can see that like the blue color, they are lane area data in Sumo. So I use those data to collect the data. And also the table showing is like observed state for each intersection. For example, here like we have a number of phases for each phases. For each intersection, and also we have like observed state for each intersection. So here I mainly use traffic jam. What is the jam ledge? Because in practice, okay, for example, here like it is the it is like a traffic war room of traffic war room. So traffic police look at those data to like to control the traffic signal. So that's why I imitate those war room configurations. So here that's why I use a traffic jam ledge as an observed state for the intersection. So that's why I do the observed state for each intersection here. These are to the observed state for the intersection. So it may be like Here, I will use AI technology, especially reinforcement learning, to control the traffic signal light. So that's why these total object state are there, object state for each agent in that intersection. So I have 6 intersection. It means 6 agents in that area, and also here are the object state for each agent. Okay. Here is the example of example of traffic signal control for the Klondike intersection. Klondike and for example, here is the Klondike intersection and Ramapo. So Klondike and Ramapo intersection are controlled by only one traffic police. So here is the example of traffic signal control for the Klondike intersection. So in real case, sometimes traffic police use like a partial phase to solve the queue space back. So here is the how they control traffic flow by using the phase switching, something like that. Okay. Okay. In my case, the objective is like we want to control traffic signal using reinforcement learning, and also we want to we don't want to stop the vehicles on that area. Actually, we want to control vehicle flow smoothly, and we want to keep loops circulating in that area. So that's why in my case, I try to use DQN and also MADDBG, deep queue network, and also multi-agent deep deterministic policy gradient algorithm to control traffic signal light in that area. Actually, we don't have good result yet. We are still trying. Because this is the ongoing work, so that's why I didn't put any result here. Okay. So I think this is my today presentation. Do you have any suggestion or questions? Yeah. Hello.
Okay. Please. Okay. Yeah. So thank you for the presentation. Are there any questions?
It's a very simple question. Those system has been deployed in the real city, not yet, or it will be planning or already deployed in the real location.
It is real world. It is real world location.
Already deployed. Does it work in the real world?
Yes, it is. It is real world location in the Bangkok city.
And do you have any estimation of the working result for the system?
Actually, okay, allow me to share some page. Okay, can you see this screen?
Yes.
Okay, so this is the this is about Ramapo More project, and it is in the closing ceremony Ramapo More project. Okay, as I said before, we have a western part, middle part, and the eastern part along the Ramapo road, right? So okay, after we try configure sensor, and also we trying to analyze the data. Actually, the objective is we want to recommend how can we solve that traffic congestion problem, something like that. So we already report about the Ramapo More project. For example, here we trying to analyze this Ramapo road area, and we after that we can find out insightful. We can find out the area using the insightful data, something like that. Okay.
Then, do you have any data for how much the traffic congestion has been minimized for your city?
Pardon, can you tell again?
Do you understand my question?
Yeah, I can catch up. I cannot catch up your voice.
Do you have any some performance result for your system about how much the traffic congestion in your city has been minimized?
Oh, okay. Okay. In the in the middle part, actually I'm still trying. And also like for example this result here we try to configure the signal control sensor, and then we compare before we install those sensor and after we install those sensor, and we compare the jam latch. How can we reduce our jam latch in that area, something like that. Okay, so this is the like analysis result for that area.
Okay, thank you.
Any other questions? Okay. Thank you very much.
Okay, thank you very much.
And let's go to the next presentation. And the last speaker is Ho Yang No, and the title is Core Network, Development and the Demonstration of AI NMS Operation Management Function. Are you ready?
Yes, I'm ready. I
Yeah.
will share my screen.
Yeah.
Can you see my
Yeah, I
screen?
can see your present slide now. So please start the presentation.
Okay, hi everyone. I'm researcher of Codeshay. My presentation title is Core Network Development and Verification of AI NMS Operation Management Function. And this is my contents. I will start the presentation in order of contents on the screen. In the 2023 Korean AI NMS technology development and validation, we developed upgraded functionality for the traffic monitoring AI engine and an AI engine for inferring fault presence. Additionally, we established fault response process for self-handling upon anomaly detection from AI. Detecting anomalous traffic involves monitoring changes in interface traffic of devices. Malicious traffic involves monitoring changes in traffic and packet variation occurring E2E. In this study, we established an optimization process for autonomous fault response in detecting anomalous and malicious traffic. We developed an AI engine to determine the presence of faults and established a process for automatic recovery for invalid faults. Additionally, we constructed a process to enable automatic recovery for frequently occurring port-down faults. This figure represents the main process of the Korean AI NMS developed over 4 years from 2022 to 2023. The managed networks includes the Korean transport network and IP backbone network. Data such as alarms, traffic, optical levels, and load rates are collected from managed device to enable proactive fault detection under AI-based systems. Additionally, when faults are identified, they trigger false ticket through the control process. Depending on the ticket type, autonomous false response processes are implemented for self-handling. This is Korean AI NMS research's progress status. There are currently 6 AI engines operating within Korean AI NMS. In 2020, we developed and validated an AI engine for analyzing root causes faults and detecting optical power degradations targeting the Korean transport network. In 2021, we developed and validated an AI engine for detecting anomalous and malicious traffic targeting the Korean IP backbone network. In 2022, we further advanced the anomalous traffic detection AI engine considering Korean's traffic characteristics and developed and validated an AI engine for detecting load rates associated with equipment. These developments were presented through Apan51 to Apan55. In 2023, we developed and validated an AI engine for determining the presence of faults. This AI engine classifies whether the results detected by AI are true positive or false positives. Feedback data from user analysis was utilized for training data. In 2020, we developed an API for managing circuits through integration with TSDN when a fault occurs in the Korean transport network. In 2021, for the Korean IP backbone network, we developed a feature for automatic handling of faults through action profile management. The action profile features allows user to configure automatic actions for specific types of faults. In 2022, for the Korean IP backbone network, we implemented daily route optimization and designed the system to recommend routes in the events of a fault. However, the final decision for route changes was left to the user, who could request change through IPSDN. In 2023, for the Korean IP backbone network, we defined an automated process for fault detection, self-optimization, and self-recovery in the events of valid faults. Of course, if users choose to manually intervene when faults are propagated to them, the automation process does not execute. This summarizes the research conducted from 2020 to 2023. And from now on, we will focus on presenting the research contents from 2023 onwards. In 2021, we developed an AI for detecting malicious traffic, but due to the limited occurrence of anomalous and malicious traffic in the actual Korean networks, there were many false positives when applied in practice. To address this, in 2023, we set up the test environment. We installed servers between 2 nodes and conducted scene-flooding attacks testing using simulated hacking tools. After a certain period of testing, we were able to collect S-flow data, which allowed us to obtain a data set of malicious traffic. The figure represents a data set of traffic collected after testing for anomalous traffic occurrences. We secured the dataset through periodic repeated testing and used it to upgrade the anomalous traffic detection AI engine. The existing threshold adjustment algorithm had an issue where values were excessively calculated due to a prevalence in the exponential operation process of the formula. To address this, we upgraded by modifying the computation process of the formula N, adding a simplified adjustmented formula. First, we prepared a validation data set including anomalous traffic, which was not used for training. And we compared this data, which is not used for training, but correct data with F1 score using the adjusted formula. And for conclusion, it was confirmed that the score was higher after applying the adjusted formula. The figure represents a data set of traffic collected after testing for malicious traffic occurrences. We secured the data set through periodic repeated testing and used it to upgrade the malicious traffic detection AI engine. We conducted a test to determine the malicious traffic status using both the previous year's model and the newly introduced upgraded model, confirming that the prediction accuracy of the upgraded model improved compared to the previous year's model. The test data sets for malicious traffic used by both models were collected from the Korean network during the same period. Malicious traffic prediction was performed by binary classification, 0 for normal and 1 for malicious. We calculated the accuracy by comparing the binary classification result with the actual ground truth. Therefore, we improved the improvement in performance compared to the previous model through feature upgrades. Key research contents of 2023 is first, real-time detection results of anomalous and malicious traffic are received using RabbitMQ. The incoming data is pre-processed in real time, and the inference engine is used to determine the presence of faults. The results determined by model are then provided again through RabbitMQ. The ticket ID serves as ID for fault identifications. When anomalous or malicious traffic is detected, a single ticket is generated. In 2022, Korean operators implemented a system where upon the occurrence of false ticket, the detection is recorded as either true positive or false positive. A value of 0 indicates true positive, while 1 indicates false positive. The provided data pertains to anomaly traffic detection fault data for each interface's in-out traffic on switches. The data structure consists of ticket ID, occurrence segment, traffic as detection, and operator feedback. This data represents the results of detecting malicious traffic by collecting S4 data. The data structure is organized into ticket ID, occurrence segment, traffic at detection, and operator feedback. For development of AI model to determine presence or absence of disability, first, top 5 models were selected using AutoML, PyCaret, hyperparameter tuning. For hyperparameter tuning, first, hyperparameters for the top 5 selected model were optimized using the tuner library. A range of generated by adding and subtracting plus minus 20% from the optimal hyperparameters. Hyperparameter tuning was conducted again within this range using PyCaret's tuning model. The 5 trained models were blended using PyCaret's blended model to create a new assembled model. Accuracy comparison was performed among the original 5 models and the model obtained through blending, totaling 6 models. The model with the highest accuracy was selected. The selected best model underwent another round of training using PyCaret's finalized model with the entire data set. The data set was split into an 8:2 ratio for training and testing. The test validation results shows an accuracy of 97% for determining the presence of malicious traffic faults and 96.5% for determining the presence of anomalous traffic faults. Yeah, this is the log that real-time AI system execution log and result log. 0-1 model is result, and 0-1 entropy is responsibility of the result. Zero is very high responsibility. This is the establishment of self-optimization process. First, real-time traffic is collected through the current IP backbone network. The second, the traffic AI engine monitors the traffic, and upon detection of anomalous or malicious traffic, the system determines the presence of faults. If a fault is detected, the system notifies the operator via email for situational awareness and allows the operator to decide whether to take automatic action. If automatic action is taken, the system shutdowns the ports of the devices where anomalous and malicious traffic was detected and completes fault handling. And this is the establishment of self-recovery process 1. Through the current IP backbone network, real-time traffic is collected, and the traffic AI engine monitors the traffic. Next, upon detection of anomalous or malicious traffic, the system determines the presence of faults. Even if it determines not to be a fault, the system notifies the operator via email for situational awareness and allows the operator to decide whether to take an automatic action. If automatic action is taken, the system identifies it as a false positive and initiate automatic recovery. And real-time syslog is collected through the current IP backbone network, and upon receiving a port down message, the system notifies the operator via email for situational awareness and allows the operator to decide whether to take automatic action. If automatic action is taken, the system resets the ports of the respective device and initiate the automatic recovery after determining its normalcy. Now, I will outline our future plans. For 4 years, research on autonomous network management technology has been conducted using AI techniques, but the developed program for research purpose was not highly refined. In 2024, there are plans to enhance the existing NMS solution by incorporating the research findings into our proprietary NMS solution, thus advancing it into an AI NMS. The existing malicious traffic detection model was developed specifically for simple loading attacks. In 2024, we plan to conduct tests with various attack patterns to collect data sets. Then in 2025, our plan is to utilize the collected data sets to enhance the malicious traffic detection AI model. This research was conducted jointly by 3 companies, as each company is responsible for different areas. So for any further inquiries about the system, please contact us via email, and we will respond through the respective contacts. Now, conclude the presentation on the development and validation of current network AI NMS operational management features. Thank you.
Thank you very much. And so, is there any questions? Oh, I have one question, and I think you compare the several classification method for detect the abnormal or disability of the network. And I guess the XGB classifier is the best performance, right?
Sorry, but this research are conducted jointly with 3 companies, so I can answer by email. Sorry.
Okay. So, and then are you going to apply the deep learning method to and the classifier?
Sorry, I didn't understand.
Sorry, and so I guess and in the future plans, you are going to improve the classifier or detector for the abnormal traffic in the network. What kind of method are you going to apply for the input the detector?
We will prepare various attacks for another sampling and another worms or such like DDoS attacks. We think it.
Yeah, so you are going to detect the DDoS attacks. That's something.
So
Sorry. What kind of I'm asking about what kind of classification method are you going to apply the, in the future plan? Then maybe the recently the many deep learning based methods are going to be applied to detect some abnormal traffic.
now I have no idea about this. Sorry.
All right, thanks. So, is there any questions? Okay. Thank you very much. So, thanks for the speakers. So I guess this is that's all for these sessions. Would you give some closing remarks? Okay. So thank you for coming to AI-driven network working groups on the. So I'm looking forward to seeing you at the next paper. Please join us. Thank you very much.